Okay, here's another example with calculating a Taylor series, but in fact there's another type of series which is similar. It's called a Maclaurin series, and it's really exactly the same thing as a Taylor series. It just happens to be centered at zero. So a lot of times the calculation of these can be a little bit easier to come up with. All right, so Maclaurin series, we will do the Maclaurin series next here. And I want to find a sixth order Maclaurin polynomial for the function cosine. Now, functions like sine and cosine are especially popular to give to students to calculate these series for because the derivatives are very easy. Arctangent, for instance, is not quite so popular because arctangent, the derivatives get successively more difficult as you move forward. So let's take a look at how we can do this. So we want a sixth order Maclaurin polynomial. Now, the last example we did fourth order. You might be thinking, wow, that, wasn't that enough work? Why are we going all the way to six? Well, you'll see in a moment as to why that's kind of necessary in this case. But we'll begin in the same way. We just kind of list out the different orders going from 0 up to 6 and start a table here. Then I will evaluate, kind of for the nth term here, I need the nth derivative. So the original function is cosine x, and these successive derivatives are pretty straightforward. So for instance, the derivative of cosine is negative sine. And then the derivative of sine is cosine, but we have this negative here, so negative cosine x. Then we would have positive sine x, positive cosine x, negative sine x, and negative cosine x. Evaluating each of these at 0, let's see what happens. So cosine of 0, if you think about your unit circle, cosine of 0 is 1. The sine of 0, however, is 0. And so these terms just kind of flip-flop here. So 1, 0, negative 1, 0, positive 1, 0, negative 1. Then I want to take each one of those and divide by n factorial. So this would be 1 over 0 factorial, which is just 1. And then 0 over 1 factorial, which is still 0. Negative 1 over 2 factorial, which there's sort of question as to whether you should actually evaluate the factorials or not. Sometimes it makes it easier to come up with the value of your series if you leave the factorials alone. You can kind of see patterns a little bit easier. So I'm going to do that in this case. If I do need to evaluate these factorials, I can go ahead and do it later. It's not a big deal. This term, of course, still is going to be 0. And then I'm going to have 1 over effectively 4 factorial, then 0, and then negative 1 over 5 factorial. Okay, so that's the coefficient. Now, if you'll notice with the Maclaurin, this polynomial term becomes easier. It's just multiplied by x, because if you're centering at 0, x minus 0 is just x. So I'm going to go ahead and declare my sixth order polynomial here and write it out. So it's going to be this coefficient times x to the nth power, so that would be x to the 0th, plus this coefficient times x to the first, plus this coefficient times, let me make that a little bit clearer, so minus 1 over 2 factorial x squared, plus 0 times x cubed. plus 1 over 4 factorial x to the 4th plus 0 x to the 5th. Of course I could leave those terms out, I'm just emphasizing. Minus 1 over 5 factorial x to the 6th. And I just realized I put that 5 factorial out of habit there. That actually should be 6 factorial. Apologize for that. You probably caught that already and trying to tell me through the screen. Okay, so then that gives us the terms, which can be simplified, of course. So this first term is just 1. The next term that shows up is going to be minus x squared over 2 factorial. The next term that shows up will be x to the 4th over 4 factorial, then minus x to the 6th over 6 factorial. The reason we used a 6th order Maclaurin polynomial is because if you use less than that, all these zeros, you end up with not very many terms in your approximation. So that's the whole reason. The Maclaurin series. We can just generalize the nth term here, so we could say that the cosine of x is defined by the series from n equals 1 to infinity of, let's see, the nth term looks like it's going to be, well, I guess they're alternating, so let's start there. So negative 1 to the, maybe I don't want that starting at 1 this time. Let's start it at 0. Because the first term is just 1, so I'm thinking that starting it at 0 is probably a better idea. So negative 1 to the n, that starts with a positive and then goes to negative and so forth. So negative 1 to the n is great. There is a factor of x to an even power in the numerator. To ensure we have an even power, I think we're going to have to do x to the 2n. And let's see if that works. So if n is 0, x to the 2 times 0 would be just 1, because that's just x to the 0. If n is 1, that would be x squared. If n is 2, that would give me x to the 4th. So that's great. That gives me the correct terms there. And then all over, I think it's going to be that same even power factorial. Because when 0 factorial gives me 1, when n is 1, that's 2 factorial. When n is 2, that's 4 factorial, and so forth. Okay, great. So that's my nth term. But the next question is, where does it converge? So to determine its convergence, we need to use the ratio test. And the ratio test, this would be a limit as n goes to infinity. Negative 1 to the n would disappear because of the absolute value. So the n plus 1th term would be x to the 2 times n plus 1 all over 2 times n plus 1 factorial. And then we would divide by the nth term, but as usual, it's easier to multiply by the inverse of the nth term. And let's see what we can do about simplifying. All right, so distributing this 2, that would be 2n plus 2. I could write this as x to the 2n, and instead of 2n plus 2, I could make this times x squared. The denominator, that would be 2n plus 2 factorial. But you know what? Here, I'm going to go ahead and simplify that. So 2n plus 2 factorial. Whenever you have a factorial, you can always pull the first term off of the factorial and multiply it by the remaining terms. Factorial, so just 1 less than this is 2n plus 1. If you take the top term off the next one, it would be 2n plus 2 times 2n plus 1 times 2n factorial. I'm going to go ahead and do that. So this will be 2n plus 2 times 2n plus 1 times 2n factorial. And then this term has the 2n factorial in the numerator, which I'm going to use to cancel. And then similarly, x to the 2n in the numerator and denominator of the other direction. Okay, x squared is the only term remaining in the numerator. I can pull that out of my limit. I don't need to worry about absolute value because squaring always results in a positive number. That would leave me 1 over 2n plus 2 times 2n plus 1. And then this limit, the denominator is changing, but the numerator is not. So as we go to infinity, this limit's going to go to 0. 0 times x squared is 0. And then when we compare that to 1, that's always a true statement. 0 is always less than 1, so that means my radius of convergence is infinity. And if my radius of convergence is infinity, then that tells me that this converges for all values. So we haven't, the previous two examples we did, arctangent and the natural log, those converged only on a small range. So let's take a look at this and see what happens and just kind of confirm visually that a function that converges for all numbers, see what that looks like. Okay, so here is my setup for cosine. If you notice here, we have the infinite series terms defined by the function that we came up with, so -1 to the n, x to the 2n over 2n factorial. And I have the function cosine here in blue, and then in green, the approximating polynomial, which in this case is just agreeing only at the centered value. And let's add some more terms so that we can see what that looks like for other values. So if I add an additional term, so adding one more term, that really increased the amount of convergence. So if I take a look at an approximation here, at different values around, say between 0 and, or -1 and +1, I'm getting pretty good convergence already, just with a second degree. If I continue that and add the next term, here's the next term. Here I'm getting really good convergence at 1. If I just continue on just slightly further, I now have convergence out to close to about 1.5. If I continue adding terms, this thing continues to converge very rapidly. And so you can see that with the approximating polynomial. And what this means is if I continue adding terms, I would get better and better approximations for cosine pretty much on any range of numbers from 0 to infinity. Now, the thing about that is if you were actually coming up with an algorithm to calculate values of cosine, you really could take advantage of the symmetry. Like for instance, you have from 0 to pi over 4, you have basically this curve, and if you flip it, you have the same curve here, you flip it again, you have the same curve here, and so forth. Or if you just looked from 0 to 2 pi, you wouldn't really need very many terms to converge between all the values from 0 to 2 pi. And then you could always use a coterminal angle to calculate cosine outside of that range. So you still wouldn't need a really large polynomial to come up with cosine approximations. But technically, it would work for any range of values.